This is a production of Cornell University.
The next reactions are basically oxidation reactions, and there's two of them that I want to talk about. One is sulfurification and one is nitrification. Sulfurification, so this is basically a sulfide versus a sulfite. Okay? In essence, this is a reduced sulfur. Okay? It was used as an electron acceptor in an anaerobic system. Okay? Here's that material. If this material gets exposed to the surface where there is oxygen and water, this is going to be oxidized. Okay? And in the process of the oxidization, it's going to basically make sulfuric acid, H2SO4. This is a strong acid. The protons are going to completely dissociate. And as a result, I'm going to be acidifying the situation. Now, this is typically associated with dredged materials. If you take estuarine materials and you bring it up and dump it on the surface because you're dredging out a soil or dredging out a channel or something like that, okay, those sulfides are going to be in that material. It gets exposed to the oxygen, and as a result, I'm going to acidify the material. When this material comes up from the bottom, high pHs, 8s, 9s, sometimes 10s. Okay? But you expose it, and after a couple weeks, the pHs start dropping, actually faster than a couple weeks, and you get pHs 4s, 3s. Now, this is also associated with what I said right here is this is the dredge material, but this is also acid mine waste, acid mine spoil. This is why all those streams in basically West Virginia and Western Virginia and Maryland are all acidic. Okay? Now, another example of this is nitrification. Now, this has to do more with agriculture, but if I start adding ammonium as a fertilizer to my soils in the presence of oxygen, I'm basically going to be making water and nitric acid, another strong acid. I got two protons for the nitrate. Okay? This reaction is associated with the soils that have a lot of fertilizer. So by fertilizing with ammonium, I am, in essence, going to be lowering my pH in my soils. Now, this might be intentional. You might actually have soils that have a really high pH, and I'm going to add it in this form rather than adding my fertilizer in this form because I want to lower the pHs. But if you're using it, it's going to happen. Okay? It's a simple oxidation reaction. The next one is acid rain. Okay? And this is the stuff that comes from combustion products, but there's also some natural sources. But basically what we're looking at is we're looking at nitrogen and sulfur gases reacting in the atmosphere with the water and making either sulfuric acid or nitric acid. Okay? Again, these are both strong acids. So I'm going to have complete dissociation. Now, rainwater is acidic. That's the carbonic reaction already. But that acidity is nothing like this. This is strong acid. This is a really strong acid. And so as a result, I'm now, when this water hits the ground, I'm now acidifying my soils. Make sense? Another source of these protons. I threw this in here just so you can have an idea. These are pHs, soil pHs, and the darker the pH, the darker the scale, the darker the color, the lower the pH. And if you think about where most of our stack emissions are from power plants in the United States, huge concentration sort of sitting in here. Downwind is where all that SOx and NOx goes up into the atmosphere and gets mixed into the soil water, the atmosphere, and basically comes down. And you can see this transect basically following the wind pattern, moving right up from that Ohio Valley straight up into the northeast. And that's acid rain. All right, the next one is plant uptake. And this is one that most of us haven't ever thought about before. But what we got here is we're looking at a plant, and the plant needs to be able to bring in to its cells, it needs to be able to bring in things, okay? Nutrients, okay? And here's my root, okay? And here's my cell walls in essence. So this is basically, imagine this is as a root cell, okay? Now, for that root cell to be able to get ammonium in, because this is the nutrient, it needs to be able to maintain a charge balance. Okay, remember that issue of salts, the solute potential? We also need to maintain this charge. Okay, and so if a positive charge is coming in, a positive charge needs to go out. Okay, and plants have what they call proton pumps, and they literally, the proton powers this pump. The proton goes out, and in the process, it brings a charge in. In this case, it's an ammonium. Okay, if I bring in 2 charges with calcium, for example, I need to pump out 2. Now, I also can use a positive charge and a negative charge to bring it in, but I need to be able to maintain that charge. And the obvious one that they use a lot of is these protons. Okay, now, if they are bringing bases into the soil solution, from the soil solution into the root material, and they're putting a proton out of the soil material into the soil solution, what are they going to be doing to this ratio? What are they going to be doing to this ratio? They're going to be increasing this, and they're going to be taking this out. And so as a result, the soil solution's ratio of protons to bases is going to be increasing. What is that going to mean to the soil pH? It's going to be lowering the pH. Make sense? Aluminum is another one. Now, aluminum is a positively charged ion. Okay, we don't think of it as a base cation. We think of it as a cation, but it's not a base cation. Okay, do you guys remember what base cations are? Base cations are not true bases, but because of their distribution, they basically act to neutralize protons. So as a result, we call them base cations. Aluminum, on the other hand, does not tend to neutralize protons. In fact, it tends to activate them. Okay? And let's actually talk about how that happens. Okay? Well, aluminum is a fairly large ion, right? Fairly large, and it's also positively charged +3, so it's a large ion, and it has a high charge. Do you guys remember the cation exchange rules? It was mass, charge, size, and complementary. Okay? Well, this one's big, and it has a high charge, which means in all likelihood it's not going to have any problems knocking things off of the colloids. It's going to sit there. Okay? And if it does that, it potentially is going to react with these protons that are in soil solution, creating a hydroxides here, putting the aluminum into the soil solution. Okay, does that make sense? All right, now theoretically that's going to reduce these protons. But when that aluminum goes into solution, it's going to react with water. It's basically going to hydrolyze it. The proton is going to go into solution, and the hydroxide is going to be pulled out, and it's going to turn into an AlOH4, or AlOH plus 2 or plus 1, depending upon where it is. Okay? Now, this can continue to react. The charge hasn't been balanced yet. It's going to continue to react with another water and make an AlOH2 plus 1 charge. It's still not balanced. It's going to react with another water, creating an AlOH3. Basically, this is a Gibbsite, at which point it's charged. The charge has been balanced, but in the process of moving from this aluminum that came from here, in the process of that aluminum balancing out, it has released 1, 2, 3 protons. Basically, acidifying the reaction, acidifying the soil solution. It's putting this into the soil solution just by it being released. Okay, does that make sense? Question?
If aluminum is so big and highly charged that it bumps cations out a lot, why would it ever be released into the solution?
Goes to that mass action where if it doesn't matter how strong you are and how big you are, if you have enough of something else, sooner or later you're going to get knocked off. Does that make sense? Well, it could be being knocked off by the protons. And as that acidity starts dropping, okay, this aluminum is going to go out. Now, by doing that, I've neutralized these 3 aluminums, these 3 protons, because they're now out of the solution. So what's happened is these guys have come out of the solution, and so as a result, I've decreased the proton concentration in the soil solution. So in essence, I've raised the pH. But this aluminum, in turn, is then going to react with the water to create more protons back into solution. So we're depending upon what the pH is of this soil solution. This reaction can go this way, or it could go this way. Okay, it can go this way, or it can go this way. If I have a higher concentration of hydroxide in soil solution, I'm going to be driving this reaction this way. As the concentration of protons increase, I'm going to be driving the reaction this way. Does that make sense? We'll talk about this is a buffering reaction, and we'll talk about this later. Okay? But what's important to remember is this aluminum is going to react with that water. These aluminums are going to react with that water, and if it reacts with the water, depending upon which way it's going to be going, it's either going to be releasing a hydroxide or it's going to be releasing a proton, which is going to be changing the proton concentration, which is going to be changing the pH. Okay? Last one, and this is where we're going to stop here because I've run out of time. Okay, the last one is parent material. Okay, and this is basically the disillusionment of that parent material. And I throw this one in because this is a really good slide. This is New York State. Totally makes sense if you think about it. Okay, these yellow lines here are basically limestone or dolomitic parent materials. Okay, glaciation basically ran this way and rolled through. Okay, now you get down into these zones right in here, you start getting to the shales and sandstones. Tompkins County, ideal location to take a look at this. What's happening to the south part of the Tompkins County versus the north part of Tompkins County? The north part of Tompkins County is close enough to this line that when it got ground through, a lot of the limestone is in the soil. But the southern part of Tompkins County, elevation starts going up, right? The glaciers are leaving the residual material from the limestones behind, and they start rolling over the shales and sandstones. So, pH-wise, the north end of the county has the parent materials that are the dolomites and limestones. The south end, the parent material of the soils, are these shales and sandstones. What does that mean pH-wise? The north end is limestone, high pHs. The south is shales and sandstone, lower pHs. Did you guys see that? What were the pHs of the soils that you saw up at Mount Pleasant? You guys remember? Shale parent material. Acidic soils. What were the pHs of the soils that you got on top of the lake plain when we were at Caldwell Field, when you were doing a mapping exercise? 6s and 7s, right? Versus 5s. Does that sound familiar? Sort of familiar? That had totally to do with parent material. Now, granted, both at the top of Mount Pleasant and at Caldwell Field, they were liming because of the agricultural purposes. But when we got out of those agricultural areas, the soils went right back to their native pHs. And that was due to this versus this. Okay? We feel comfortable with this? Sorry.
This has been a production of Cornell University, on the web at cornell.edu.